now, measurements and feature. So as I said, deep learning is about doing machine learning on high-dimensional space. And as examples of high-dimensional space, we can take as an example text. So I can retrieve the whole Wikipedia corpus, and I will pre-process this raw information, this HTML data, to bring it to something that is close to my example XY structure that I've just presented. So you define your test, performance metric, and now with the data, you will define one example, what is the X, the input of my model, and the output. And you should be able to know the number of examples that you have in your data. For text, it will be the number of sequence. And you should also be able to tell the maximum length of a sequence, the minimum length, maybe some statistic. On average, the length of my text that I'm giving to as an input will be around 10 words, as an example. And other statistics, like the term frequencies, and also the encoding. Is it encoded in UTF-8 or something else? For image, if your test is the X is one image, and I want to predict something about this image, the number of examples will be the number of images. And you should also know the width of the image, the height, and the number of channels. Are you considering the RGB channel of this image? And also you should know the encoding, because the way we will pre-process the image to bring it as an input of the model will also depend on the encoding. Finally, if you have a test where the input is a video and the output is something about the video, a video is made of images, so you can see that one image now is not an example. It's the number of videos that you want to use for learning. That will be the number of examples. But again, you will have the width of the frame of one frame in the video, the height, the number of channel, and maybe you want to use audio, the subtitles, and you should know the codec so that you are able to process the video into a data that will be compatible with the input of a model. And you have graph. Graph can be represented in different ways, and dictionary too, with files in JSON structure that you can find properties that you want to use to do the pre-processing. So when you meet an expert that will help you with your data, be sure to have at least some of these information in mind. Don't say I have a lot of data. It's not precise enough. It's about the structure of the data. Okay, so the concept of a representation. Now it's a little bit more abstract. We will use the term representation over and over this week, but let's try to understand what we mean by representation. So representation is some information that I gathered from reality that I am implementing in a medium supporting the transformation of this information. And one to understand this definition was René Magritte in The Treachery of Images. And he created this art piece where he says, "Ceci n'est pas une pipe." This is not a pipe. And the reason why is that he was looking at the actual object in reality, and he got some representation into his head, in the neurons of his brain, and he was able to put the representation on paper. So the first medium was the neuron in his head, and the second the medium was the paper. And now you can manipulate these representations as you want. You can maybe modify the shape of the pipe, etc., to obtain new representation. But the way you transform these representations are independent of the initial object in reality. So always have in mind that even if you are using data represented in some way, the data represents something in reality, and maybe the two are not the same after some processing. And people tend to forget about it. It's like the data is the truth in the universe. No, the data can be deprecated after some times, and you must acquire new data because reality changes. So a local representation is where, so I have some information, and this information are organized in some way. So the input of a neural network will have these little circles that we call processing unit, and each processing unit will be associated to one specific feature with a definition, and maybe the physical unit. And we call it local because here I can see that the feature petal width, expressed in centimeters, is associated to this processing unit in my artificial neural network. And it's easy to interpret. I can say this component represents the petal width. And you have also distributed representation, where you completely lose this information, where you can see this physical unit, this processing unit, is actually merging information from my local representation here. So the semantic associated to this processing unit is a mix of petal width, petal height, and sepal height. And if I give you a numerical value associated to this processing unit, it's not interpretable anymore. The local distribution have been distributed into one into one processing unit here. Distributed representation are much more efficient than local representation, and we'll see an example. And they are used in artificial neural network. So that's why you are seeing a lot of papers trying to interpret neural network and trying to know how the model is solving the task by looking inside the network. But with distributed representation, it's super hard to know what the numerical value associated to this node is really encoding. At the input and the output, it should be interpretable. And why I'm using these terms like the data processing unit and how it is implemented, it's because the first artificial neural network was a machine, actually. It was this machine called the Mark I perceptron, created in 1958. The local representation was given as an input of this machine with some wires, and then the wires were creating the distributed representation by combining different wires from different local representation to only one processing unit. And you can see how complex this machine was with all the wires everywhere. Now we are simulating this kind of machines on a computer. We still use the vocabulary associated to it, but now everything is simulated in PyTorch or TensorFlow. But there were actual machines at the beginning of AI. So one example of how to create local representation for text. So for text, I would have a little corpus of 3 sentences. We live in Montreal, we live together, we like winter. And I will use something called tokenization to bring it to a representation that I can use as an input for my model. Tokenization can remove capital letters and also split the words according to the space between the words. So I obtain this intermediate representation. And the last step, I will use a dictionary, where for each word, I will have one identifier. So period will be associated to 1, we to 2, winter to 3, together to 4, etc. And so I can do my mapping to obtain this representation. But is it a good representation? In fact, the integers have a natural ordering. So 7 is greater than 5. And if I look here, I will say that in is greater than live. And it doesn't make any sense. The words cannot be ordered as the integer can be ordered. So instead of using integer like 25701, I will use another kind of encoding called the one-hot encoding. And a one-hot encoding will be a binary vector like here, where the number of elements of this binary vector will be the number of elements in my dictionary. Here I have 8 elements because of this token. Oh, and I'm sorry, I did not explain what is this token. If my tokenizer reach a word that is not in my dictionary, I can still use the unknown token to encode that there was a word there. But because my dictionary is not big enough, I cannot use an identifier. Usually in natural languages, we will have dictionary of the size of something between 50,000 to 100,000 if we use tokenizing over spaces. There are other ways to do it more efficiently. And if I go back to my one-hot encoding, so the number of elements in my binary vector is the number of elements in my dictionary. And here I want to encode 2, so I will go at position 2, which will be 0, 1, 2, and I will assign this bit to 1, and the rest will be 0. So I've just changing the encoding from integer to one-hot encoding. And this encoding works better as an input for a neural network, because the network will not use the ordering of these numbers as a feature. Also, we can do other transformation on the local representation. So for each, if I use a vector to represent a local representation, I can normalize each component of this vector independently by using min-max feature scaling. So if I have a pixel between 0 and 255, its max will be 255, its min will be 0, and I can rescale all the pixel intensities to between 0 and 1. And this order of magnitude, 0 and 1, works better with neural network than an order of magnitude between 0 and 255. It's better to use a small range of values than range of values going to hundreds or thousands. And standardization is very similar. For each feature, I can estimate the empirical mean of this feature on my training set, and I can estimate the empirical standard deviation on my training set, and I can normalize it like this. So the take-home message of this presentation is that, first of all, machine learning is a subfield of artificial intelligence, and deep learning is also a subset of techniques in machine learning to implement some ideas that we will see tomorrow. There is a methodology that exists to prevent the learning algorithm from cheating, and we saw one essential step, which is cross-validation that we must do to better evaluate the model, but there are also other tools to verify the model. And also, what we saw just now is that data should be independent and identically distributed. And we will come back to other examples very soon.